Okay, so finishing up example 1, we're going to take a look at equation C next. So this one looks a little bit different. We've got a fractional exponent, so we're going to explore that. And notice that the equation for C and the equation for D are very similar, just that the fractional exponent is different. Okay, so part I is asking us to find the critical points, which means I need to find the derivative of this. So we've got a chain rule here. I'm going to bring the exponent down out front, leave the bracket, leave the inner function alone, and then subtract 1 from the exponent, and then I'll multiply by the derivative of the inner bracket, which is just 1. And so I can simplify this, bringing that bracket down to join the 3 in the denominator, and then the 1/3 exponent is the cube root. So here's our first derivative, and this is going to help us find those critical points. We're going to set this equal to 0, and we're going to figure out where does it not exist. So when I'm looking at this guy equaling 0, I've got a fraction equals 0, and remember that in order for one fraction to equal 0, the numerator has to equal 0. So this is going to equal 0 when 0 equals 2, which is impossible. So therefore, there are no solutions. I'm also going to check out, well, when does the first derivative not exist? So when I talk about something not existing, some of the functions I know that have restrictions are denominators. So whenever I have an x in the denominator, I might have a restriction. Whenever I have an even root, so like a square root, I know that I can't square root a negative. So I would also be investigating that. If I were in another unit, I might investigate a log function. I know that the domain of the log function is restricted as well. So I'm thinking through those kinds of things. So in this unit, it's mostly going to come from our denominators and our square roots. So in this question, I do have a denominator. So the function will not exist when the denominator is equal to 0. So that's kind of what I'm thinking in my head. I wouldn't normally write that down. I would just set the denominator equal to 0. And so I'll divide both sides by 3. And then to move the cube root over, I'm going to cube both sides. But when I cube 0, I get 0. And then I'll move the 4 over. And so this derivative is not going to exist if I put a 4 into the denominator, and you might have been able to see that from the start. So I only have one critical number that I need to include in my chart, and eventually I'm going to need to find the y value of that as well. So across the top of my chart, just 2 intervals with that critical number in the middle. All right, then we're going to pick a test point. And then we'll find the sign of the derivative. Okay, so picking a test point between -infinity and 4, I always pick 0 when I can because it's usually a nice easy one to plug in. This one, it doesn't actually make my life a whole lot easier. I'm plugging it into the derivative, so I'm going to use this simplified version when I do that. Again, at this point, I haven't moved anything across the equal sign. This is still the entire derivative. So I'm plugging in 0 underneath the cube root here, and so I've got the cube root of -4. Now I can cube root a negative, and it gives me a negative answer. You can check that on your calculator if you're not sure. So this is going to be a negative. So I end up with +2 divided by +3 times a negative. And so overall, that's going to give me a negative answer. Then moving on to 4, I know that when x is equal to 4, the derivative does not exist. And so we'll put this short form dne. You'll see this often in math. Does not exist. All right, and then we're moving into the interval, picking some number bigger than 4. Again, I'm going to pick something really big. You could try to figure out a number here that's easy to cube root as well. What I'm going to get underneath this cube root is 96, and when I cube root 96, that will be a positive number. So again, I've got positive 2 divided by positive 3 times, and then the cube root of 96 is some positive number. So overall, that's also equal to a positive. So what I have here is that my derivative does switch sign, and I want to double check when I'm thinking about this. I do want to double check if x equals 4 is an actual point on the original function, or if it also does not exist. If it also does not exist, then I've got a vertical asymptote here. But if it does exist, then I might have that cusp or that scary slide. So I'm going to come back up and consider putting 4 into this equation, and f at 4 would give me 0. So it does actually exist there. And so what I'm going to see is a cusp at this point. So it's not a flat tangent. The tangent is a vertical tangent at this point. But I see that I'm decreasing coming in, so this is like a negative slope, and increasing coming out. And the point exists, but it's not a flat spot. All right, so we're going to use that information at the bottom here to help me sketch the graph in part B, but let's finish up part A. What I notice for part A, thinking about the first derivative test, is that the first derivative went from negative to positive. So it did switch sign. And so that one tells me, again, I've got a negative slope coming into a positive slope. I've got a minimum here. And I've forgotten to find my y value. So I need to go and find my y value here. I'm going to plug it in. And I said it out loud, but I didn't actually calculate it. So I do need to find the value of the function. So finding those points. Plugging 4 in. I get 0. So I've got a minimum there, but I do not have a flat tangent line. So it's not like a soft curve at 4, 0. It's going to be a cusp. All right, so part B asks me to find the x and y intercepts. So setting my original equation equal to 0, and then I'm going to solve. So bringing the 2/3 to the other side as an exponent, it becomes 3/2, right? I flip the exponent. And so that's still just 0 though. And so x is equal to 4 is my x-intercept, which we kind of already knew over here, right? When we found the critical point, we were just checking to see if there was more than one. When I do this, I am squaring this side, so it's a cube root being squared. So I am doing the plus minus here. When the numerator is even, I have to consider the plus minus, but it is 0. So I didn't have to worry too much about that. So to find my y-intercept, I'm going to set x equal to 0. And I'm remembering that the 2/3 is the cube root of -4. And you can either square the -4 first or cube root it first and then square the result. So I'm going to extend this and I'm going to square the -4 first. I'm squaring the negative as well, but it would be okay for me to cube root a negative number. That's fine. So I've got the cube root of 16, which, since I'm going to graph it, I'm going to just change that to a round decimal. It's about 2.5. And so I've got my points that I need to include on my graph. So again, I know that the x-intercept is at 4 and the y-intercept is at 2.5. And the x-intercept is also my critical point. So I actually have all the points on here that I need. I just need to show that the graph has a decreasing or a negative slope all the way coming into 4, and then not coming in flat. I'm just bouncing back out. And this one's going to kind of curve in and curve out. And I know that from some experience that it's not going to look like an absolute value function. It's not going to come straight in. And you'll get used to that as well. When you see that 2/3 exponent, you're often going to see this curve in and out. All right, oh, we're moving on to D though. So the equation for D, very similar to above, but now we've got a 1/3 exponent. So I'm going to take the derivative because I need the critical points. And then multiplying by the derivative of the inner bracket is just 1, and then I can simplify this. And here I can put the squaring again on the inside or the outside. If you put it on the inside, you do need an extra set of brackets around the x minus 4. So we've got our first derivative. In order to find the critical numbers, I need to set the derivative equal to 0, or I need to look for where does the first derivative not exist. All right, so if I want to set my first derivative equal to 0, I'm thinking about, I'm just writing this a little bit different than I did last time in case you like this way better. So I'm actually filling in the equation for the first derivative, setting it equal to 0, and then I'm taking the denominator. Since I have one fraction equals 0, I can take that whole denominator and multiply it up on the other side. So I'm taking this whole thing, multiply it up over here. And what I get is 1 is equal to 0 times the bracket. But 0 times the bracket is just 0, and I get 1 is equal to 0, which is a nonsense statement, and so therefore there are no solutions. All right, so now we need to talk about, well, when does this thing not exist? So again, I don't have an even root, so I don't have to worry about square rooting a negative or anything like that. I just have to think about when is the denominator equal to 0. So again, I'm going to bring the 3 over and divide it to the other side. And then you can go in either order here. So because I have squaring, I could do the plus minus square root. And that's 0. And then I can take, instead of cube rooting, I can raise that to the power of 3 on the other side, which is still just 0. I'm really breaking this down. I'm okay if you skip a couple of these steps in here. And then this gives me x is equal to 4. So I've got my one critical number, and I'm going to set up my chart. So far, this should be feeling like a lot like the last question, but there are going to be some differences now. All right, we'll pick our test point, and then we'll figure out the sign of the derivative. All right, picking a number between negative infinity and 4. Again, I'm going to pick 0, and I'm subbing that into my first derivative. So I'm looking at this one right here. So I've got a positive on top, and then I've got positive 3 times. If I plug 0 in here, I'm going to get 0 minus 4, and then cube rooting that is a negative. So I've got a negative number squared. So I've got a positive 1 divided by positive 3 times a negative squared. And so all together there, I'm actually going to end up with a positive number. For x equals 4, we said that that came from when the first derivative does not exist, right? That's how we came up with that. And then picking a number bigger than 4. So again, you can pick whatever you like. Let's say we pick 100. If I plug it in here, underneath the root, I'm going to get positive 96. When I cube root positive 96, I get a positive. So everything is positive here. I got positive 1 divided by positive 3 divided by the cube root of 96 squared. And so overall, this is positive. So this is where we see our big difference here. I do not switch sign at this critical number. So I do not have a maximum or a minimum. I have to see a switch in sign here. What I also notice is that because the first derivative does not exist here, 4 is a critical number, but it's not flat. I'm going to go and find the y value because I do still need to plot that point. So plugging 4 into the original equation, I'm going all the way back up. I can see here that I get 0 to the 1/3, which is just 0. So I still have that same point here, but this time I'm increasing coming in and increasing coming out, and I have that vertical tangent at this point. And this is what we call that scary slide. So we're going to write our summary sentence, and then we'll get into the graph. So this graph has no maximums or minimums at all. All right, part B, or sorry, part I should say. We're going to find the x-intercepts. And again, I'm dealing with the original function here now because I'm talking about graphing actual points. So I set it equal to 0. And I bring the 1/3 over, it becomes 0 cubed on the other side, which is just 0. And x is equal to 4. Which we already knew, right? When we plugged in 4, we got a y value of 0. But there is only one of them. That's one of the things that we were looking for. Here I didn't have to worry about the plus minus, right? Because it was a 1 in the numerator, so I wasn't actually taking the square root of both sides at any point. So for the y-intercept, I'm going to set the x value equal to 0, so subbing in f at 0. So I'm going to end up here with the cube root of -4, which, don't forget, I can take the cube root of negative numbers. If I multiply about -1.6 times itself 3 times, I will get about -4. So I did round my answer there so I could graph it. All right, so let's take a look. What does this look like? And again, remember, this whole chapter is about building these ideas as we go along. So we're going to get a better and better picture of these graphs as we go. Okay, I know that my x-intercept is here at 4. It's also my critical point. So this is like a special spot on my graph. And then I have my y-intercept at -1.6. And what's happening at -4 is the slope does not exist. And I know that I have a positive slope coming in and a positive slope coming out. So my whole graph is kind of heading up to the right. But I have a vertical tangent at x equals 4. So it kind of comes out like this and then down like this. So there's my kind of scary slide. I popped down and hurt my bum. All right, and that's what we have for part D. We're going to move on to example 2. All right, example 2 says find the critical points. We've got this rational function here and determine whether the points are maximums or minimums. That's what we mean here by local maxima and local minima. Explain why -2 is not a critical number, even though the derivative at -2 does not exist. So it's kind of like a second part to this question. So I'm going to start with the first part, finding the critical points. I'm going to take the derivative. I've got a quotient rule here, so I'm remembering that I've got an f function over a g function, and the quotient rule tells me to take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So the derivative of the top is 4x, and then I multiply by the old denominator. I don't change anything. Subtract. This time I don't change the numerator, and I take the derivative of the denominator. The order matters here, right, because it's subtraction. And then squaring the old denominator. All right, so we've got our derivative. I'm going to simplify it a little bit because I know that eventually I'm going to have to set it equal to 0. And I actually want to keep the derivative all together so that when I'm doing my test points for my interval, I have the whole thing together. I don't want to eliminate the denominator right away. So I'm going to simplify the numerator. So collecting like terms there, and then I can factor out in the numerator. And nothing cancels. This is my y prime, and I'm going to use this guy in the interval chart. I have not removed anything or moved it to the other side yet. So two different things I need to check. When does y prime equal 0? Well, when the numerator is equal to 0. So you can write the entire thing if you want, but I'm okay with you going right to the numerator has to equal 0. So this line here is going to be optional. Remember, when I have one fraction equals 0, I can just bring the denominator up. If it was two fractions, I can't do that. I can't just say that the two numerators equal 0. I have to come up with a common denominator first. And so now I can split this. I've got two solutions here. So two flat spots on my graph. Now we're going to figure out, well, when does the derivative not exist? And the derivative does not exist when the denominator is equal to 0. And so I'm going to square root both sides. I'm square rooting 0, so the positive and the negative square root is still just 0. And x is -2. Now, -2, the second part of the question says to explain why -2 is not actually a critical number, even though the derivative, when I plug in -2, does not exist. And that's what we just figured out here. The derivative does not exist when x equals -2. So when we scroll back up, we want to figure out, why is that not even a critical number? Like we just figured out that it was. And it's because when I look at the original function, I look at that denominator and I notice that -2 also does not exist on my original function. So I'm going to write that down here. This is for part B. So I've written here, x equals -2 is a restriction for the original function. So that means it's not actually in the domain, so it can't be a critical point, right? Because there is no point there. Another way that I could have phrased that first line is I could have said x equals -2 is not in the domain of the original function. Therefore, it's not a critical number. But we still use it. So even though it's not a critical number, because it's a restriction in the original function, I'm going to use it in my table. So I still have three values, -4, -2, and 0 as I go across. Like you're hoping there's never more than 3, right? That's a big one. All right, we're going to come up with our test point. And then the sign of the derivative. They haven't asked me about intervals of increase and decrease, so I actually don't need any of this stuff here at the bottom. But you can put in a column for the behavior of the f at x graph if that helps you kind of sort out your thoughts. Just don't forget your therefore statement. All right, so we're using the derivative. So I'm coming back up here and I'm looking at this equation right here in my chart. So I'm going to pick a number between negative infinity and negative 4. Let's say I pick negative 100. Then this first factor, 2x, will be negative 200. So that's a negative times, in the bracket if I put in negative 100, that will also be a negative. So the numerator is now a negative times a negative, and then the denominator, the bracket, will be negative, but I'll be squaring it. So I picked negative 100. I get negative times negative over negative squared. And all together there, I've got 4 negative signs, so they all pair up, and that means overall I'm going to end up with a positive answer. All right, now I don't need to check negative 4. I came up with it from the derivative being equal to 0, right? That's where we came up with this. I just noticed a mistake in my chart. I'm talking about f at x all of a sudden in my chart, but there is no f at x, so I should have y prime here. All right, next we're picking a number between negative 4 and negative 2, so probably you're going to pick negative 3. We'll go back up here, plug in negative 3. The first factor is going to come out to negative 6. So a negative, and then in the bracket here, that'll be a positive. In the denominator, it's going to be a negative squared. So altogether, a negative times a positive times a negative squared. And here in the bottom, that's going to turn into a positive, and then in the top, I'm going to have a negative. Negative divided by positive is a negative overall. All right, negative 2, I don't need to check. It does not exist, right? That's where we came up with this. And remember, it actually doesn't exist for the original function as well. So if you did want to add a column for y, here I'd be putting does not exist, whereas with the critical number negative 4, I would be saying, like, I have a flat point there, or a flat tangent there. All right, picking a number between negative 2 and 0, you're probably going to pick negative 1 unless you love fractions. I'm going to come back up and put negative 1 in here. I get negative 2 at the beginning, and then times a positive. In the denominator, I'm going to get a positive squared. So overall, when I multiply this all together, I am going to get a negative answer because there's nothing to pair up with that single negative. Again, I don't need to check 0. I know that I came up with it from when the derivative is equal to 0. So again, I know that there's going to be some sort of flat point there. Maybe it looks like that flat part of a cubic, or maybe it looks like the flat part of a parabola. I'm not sure yet. All right, picking some number bigger than 0. Again, I went with 100, but you could pick 2 or 1 if you like. We're going to come up here and plug that into my derivative. So I'm going to get 200, so a positive times, again, if I put 100 in this bracket, that's a positive. 100 in this bracket is also a positive squared. So everything's positive here. All right, so we're going to try to draw some conclusions here about whether I have maximums or minimums. So sometimes it can be helpful to draw that here I have an increasing slope, here I have a decreasing slope, here it's also negative, I have a decreasing slope, and here I have an increasing slope. And so sometimes this helps me imagine, here it's flat, and here it's flat. I can see here it's going to be a maximum, and here it's going to be a minimum. So I just have to write a statement here. Don't forget that this doesn't exist, so it's probably a vertical asymptote through this line here. They did ask me for the y values here. They said critical points. So I'm interested in these two x values for my points. Sometimes I get to skip this step, don't forget. If they just had asked me for critical numbers, I would skip this step. No function notation, so I actually have to like write at x equals -4. I'm going back to my original function for this, not the derivative. This is the one they gave me in the equation or in the question. So I've got my 2 critical points now. I'll write my conclusion about the maximum minimum. So I'm looking in the chart here at -4, it's switched from positive to negative, and so that tells me that there's a maximum there. And I'll grab my y value over here, it's -16. Then looking at my next one, I'm moving from negative to positive, so that's going to be a minimum on my graph. Okay, this one did not ask me for a sketch, but you could type this original equation into Desmos if you'd like and take a look. It looks something like, I'll just do a quick sketch so that you have a good grasp of this one. Oops. Remember that the original function does not exist at -2. It's a vertical asymptote there. I know that there's a point at 0, 0 and a point at -4, -16. This point at 0, 0 is a local minimum. It kind of looks like this. And then this point here at -416 is a local maximum. It kind of looks like this, and then it gets closer to that vertical asymptote, so this guy keeps coming down. And with this question, you might have noticed at the beginning that the degree of the numerator was 1 greater than the degree of the denominator. So there's actually also a oblique asymptote, and we'll be working on that in our next lesson. So there's actually like a line here that it's getting closer to. So I haven't done a good job with this one here, but it kind of looks like this. You weren't asked for a graph in this question, that's why this one's so messy, but I just wanted you to have a good sense. All right, good luck with that homework.